Hello all, today we are going to start a new chapter concerning the electric field. We all remember from last year that any charged objects interact with each other according to Coulomb's law. We also know that this interaction is called the electrostatic force. We know also that charges of the same sign repel each other, whereas the charges of opposite sign attract each other. Now, this electrostatic force of interaction between the two charged objects is given by the relation F is equal to K multiplied by Q and Q prime taken in absolute value over the square of the distance separating them. More specifically, F represents the electrostatic force, which is expressed in newtons. We have Q and Q prime, the charges of interacting bodies. And of course, we have d, the distance separating the charged objects, expressed in meters. And finally, we have the Coulomb's constant, which is calculated by the ratio 1 over 4 pi multiplied by epsilon, where epsilon is a Greek letter that represents the electric permittivity of the medium. It is a constant that describes the properties or the electric properties of the medium where the experiment is taking place. Now, for example, for vacuum, epsilon 0 has the value 8.85 multiplied by 10 to the power to the minus 12. Now, it is expressed in Coulomb square over Newton per meter square. Finally, we can get for vacuum our famous Coulomb's constant, which is K equal 9 times 10 to the power 9, taken in SI units. Now, let's move to the main idea of the chapter, which is the electric field. What do we mean by electric field? Let's start with the qualitative definition. In any region of space, we can say that there exists an electric field if and only if by placing a small tested charge, and this small tested charge, if it was submitted to a force F, we can say that in this region there exists an electric field E. Now let's move to the quantitative definition of the electric field, or the formula, where we have the electric field vector is given by the ratio of the electrostatic force over the small tested charge Q. In other words, in order to determine the electric field strength or its magnitude, we may calculate the ratio of the magnitude of the electrostatic force over the absolute value of the small tested charge Q. And we also know that the electrostatic force may be calculated from Coulomb's law, which is given by the formula F equal K multiplied by the small tested charge Q taken in absolute value. And here we have a second charge, which is capital Q. Actually, the presence of the electric field in the considered region is due to the presence of this capital charge Q that is interacting with the small tested charge Q placed at a distance d away from capital Q to get the electrostatic force of interaction. Now, by substituting the electrostatic force in its expression, we may get the expression of the electric field strength, which is E equal to K multiplied by the absolute value of capital Q over D squared, where we have in this relation the capital Q, which is the electric charge producing the electric field, which is expressed in coulombs. We have K, the Coulomb's constant, and of course we have D, which is the distance from capital Q at which the electric field strength is calculated. And finally we have capital E, which is the electric field strength or magnitude at a distance D from the electric charge capital Q. Now let's move to the representation of the electric field vector. If the charge producing the electric field was positive, then in order to represent the electric field vector, we represent it away from this charge Q, or in other words, outward. And if the charge producing the electric field was negative, then the electric field vector is represented towards capital Q or inward. Now back to the electrostatic interaction, we should know that if the small tested charge Q was positive, then the electrostatic force vector and the electric field vector have the same direction. And if the small tested charge placed in the electric field region was negative, then the electrostatic force vector and the electric field vector have opposite directions. Electric field lines. What do we mean by electric field lines? Actually, electric field lines are lines that indicate the existence and the direction of an electric field. For example, if the charge producing the electric field was positive, then the electric field lines are directed outward. And if the electric charge producing an electric field was negative, then the electric field lines are directed inward. We should know also that the electric field vector is represented tangent to these lines. An important remark that we should know that electric field lines don't intersect at any point. Finally, the uniform electric field. Actually, uniform electric field is a special type of electric field that can be produced between two charged metallic plates having opposite signs. The main property of this electric field is that the magnitude and the direction of this electric field vector is the same anywhere between the two plates. And of course, as we can see in the figure, the electric field lines are parallel to each other. This is a special type of electric field that we are going to talk in details in the next chapter. Thank you.